Alright, in this video we're going to be looking at matrix inverses and seeing how the idea of a transformation can really tell us by looking at properties of linear transformations whether or not a matrix A has an inverse. We'll be tying this into the related idea of something called the determinant of a matrix, and at least for matrices of dimensions 2 by 2 and 3 by 3, we'll have a chance to see some calculations of determinants, and we'll return back to these when we cover chapter 3 in lay. Alright, in general, so far when you guys have been asked to compute inverses, most of the time you guys have used the technique that if A can be row reduced, or is row equivalent, to the n by n identity matrix, that means that A inverse exists. And the way you've been computing it has been to look at the matrix obtained by setting A and the identity matrix next to each other, and row reducing to find the identity matrix where A was, and looking to see what pops out here. So the matrix that we see here is an n by n matrix, and the properties that it's going to satisfy in general are that matrix times A inverse is equal to A inverse times A is going to be our identity. So we'll see at the end of this lecture a long list of equivalent theorems, but this so far has been the kind of computationally heavy way that we've dealt with it, even in relatively simple cases like 2 by 2. So what we're going to look at today is, in general, assume we have a matrix A, B, C, D. It turns out a sufficient condition for A inverse to exist if AD minus BC is not equal to 0. So this, for a 2 by 2 matrix, actually has a special name. This is called the determinant of a 2 by 2 matrix. So we get it by, again, just taking the product of the entries on our diagonal and subtracting the product of the entries on our anti-diagonal. So this is going to be our condition for A inverse to exist. And furthermore, one of the nice things that we get is A inverse we can actually compute. We'll compute it by taking initially our transpose. Make this look a little closer. So our transpose of our matrix just exchanges our entries B and C and leaves our A and D fixed. The way we're going to obtain our inverse is we look at 1 over the determinant, and we can actually, for each of these entries, let's say to calculate the entry on our inverse in position 1, 1, 1, we'll cross out the first row and the first column and look at what's left over. So similarly, if we want to compute the entry in our second column and first row in our determinant, we would cross those out, and we'll actually put a negative B here. So there's a clever reason all of this works that we'll get to see a little later, which is a procedure to remember how to find these things. To get our entry here, we cross those out and put a negative C there, and we cross out our second row and second column to get a positive A here. So this formula is the general determinant for a 2 by 2, or the general inverse of a 2 by 2 matrix using our determinant, and this matrix is actually going to be called the matrix of cofactors. And we'll get to see a little later, again, what a cofactor matrix means for a general matrix. In general, just as a reminder, this gave us a nice quick formula for calculating our determinant of a matrix 2 by 2 matrix in general, which is the determinant of a 2 by 2 matrix. So some A, B, C, D is just the product of our entries on our diagonal minus the product of the entries on our anti-diagonal. And one of the nice things that we're going to take away from this is we actually have a nice way to now interpret what the geometric meaning of having an inverse is. So we've seen before that one way to examine the matrix of a linear transformation was to start with a unit square, so the vector 1, 0, should make this a column vector, so the vector 1, 0 and 0, 1, and our matrix A will send, if our matrix has column vectors A1 and A2, it'll send our unit vectors to their images over here. It'll send 1, 0 out to A of 1, 0 is exactly our first column vector, and it'll send the image of the vector 0, 1 out to the vector A2. So we can identify whether or not a given matrix has an inverse by using this determinant formula. So the determinant of A is A11 times A22 minus A12 times A21. Interestingly enough, this is precisely the area of the parallelogram spanned by those vectors, with edges A1 and A2. So an interpretation for the determinant is actually precisely the area of one of these parallelograms. And we can identify when a matrix has an inverse precisely when this transformation is 1 to 1, or when our vectors weren't sent to a parallelogram of area 0. So this idea that the determinant of A non-zero if and only if A inverse exists, that's really telling you that we have some way of recovering our original set of vectors, rather than everything being smushed down to something of volume, or sorry, of area 0. In the 3x3 case, things start to get a little more complicated in terms of actually rapidly computing the inverses, but given some big matrix, let's say A, B, C, D, E, F, G, H, I, I'm going to use the notation Aij to be the matrix that we obtain by deleting the ith row and the jth column from A. And so this is a submatrix. So for example, A11 we would obtain by looking at our matrix and erasing row 1 and column 1. So A11 would be the smaller matrix EFHI. If I wanted to obtain the matrix 2, 3, again I cross out my second row and my third column, so without continuing to write everything out every time, it's ABGH, and so on. So an alternate formula for our inverse of a matrix A is going to be the following. We'll let bars around a matrix Aij, in this case, mean the determinant of the 2x2 matrix of these cofactors. So, for example, A11 would be EI minus FH. So this is a sample. They would call this a cofactor. And our formula for the inverse of A, making use of these, is I have A inverse is 1 divided by the determinant of my 3 by 3 matrix, which we'll see how to compute that in just a second, times the matrix of all 9 of my possible cofactors. So there's my first row. Here's A22, A23, A31, A32, and A33. So the only thing we haven't quite gotten yet is how do we compute the determinant of a 3 by 3 matrix? The way we'll do that for something like this is we'll actually look at our entry in our entries along this first row, and it'll be A times the cofactor A11, so that's smaller determinant, minus B times the cofactor DI GF, so this 2-1, plus C times that third cofactor coming out of our first row. So for our matrix here, they call this expanding along cofactors. This will be A EI minus FH, which is our cofactor here, minus B times DI minus GF, plus C times DH minus EG. So this is our formula for our determinant of a 3 by 3 matrix. So this involves computing a decent number of these little cofactors and this one long determinant, but it gives us a closed formula for something that otherwise we'd have to spend a decent amount of time row reducing. In the same way that we could interpret our determinants of a 2 by 2 matrix as measuring the area of the transformation of the unit square, now for 3 by 3 matrices, we can actually picture this as telling us for our unit cube, which is not so easy to draw very prettily in this, when we transform our unit cube by some 3 by 3 matrix, we'll get a parallelepiped of some sort. I'm going to not draw my axes out of accession to lack of ability to do this. The volume of the image of each of our of the span of these E1, E2, and E3, where these are our 3 unit vectors. So the volume of the parallelepiped span by those is precisely the determinant of our matrix A. So you actually have inside your course notes access to a American Mathematical Monthly, where they give you some nice pictures of this geometric interpretation. And finally, let's wrap this all up just to get this into one big theorem, which is putting the determinants aside for the moment and just talking about all of the different equivalent ways of looking at invertible matrices. There are a lot. I think they have A through L inside your text, but so far we've seen that given an invertible matrix, it's row equivalent to the identity matrix. So this is precisely the calculations that we've been using to try to identify what our inverse actually was. So our inverse exists if and only if we can construct it using this. The idea that we have an identity matrix, or rather that A is row equivalent to the identity matrix, tells us that A has to have pivot positions, so n full pivot positions in this n by n matrix. Similarly, tied to this, we know that this matrix A, as a linear transformation, has to be injective. So any equation of this form, where we have a homogeneous equation, has only the trivial solution. And on that same note, since these are equivalent things that we've already seen in earlier videos, the columns of A being linearly independent is equivalent to the homogeneous equation having only the trivial solution. So all 3 of these are things that we've looked at before in other classes. Finally, sort of tying the last of these things together, we have, again, no matter for things other than the homogeneous equation, we also know that this equation always does have a solution. The columns of the matrix, since they're linearly independent and there are n of them, turns out that guarantees that they'll span our set. So this is tied to that linear independence. Thinking about these things and their determinants that we looked at before, and this idea of our linear transformation having full volume, meaning it mapped as a unit square, it mapped the square to some parallelogram with volume. That's this idea of mapping R2 to R2. So it didn't map to some subset, it really hit everything. And these down here, sort of continuing seamlessly into the next one, these are precisely the properties of invertible matrices that we've been using. That an invertible matrix acts acts on some vector equation like this. We could actually multiply by our inverse that they're calling C here. This A inverse times A, after using our associative property for matrix multiplication, our A inverse times A is the identity. So we're able to recover a fixed solution to one of these matrix equations using inverses. So this property of inverses in many ways work very similarly to inverses in the rationals, in that we're able to multiply by a matrix inverse to take us back to some identity or 1 in whatever ring or field we're looking at. And one of the nice things, we'll come back and look at this later, if A has an inverse, that also means that A transpose has an inverse. So that'll be nice later when we're looking at properties of row spaces and column spaces and seeing how the transpose and the matrix itself are very closely related. And one extension, again, that we'll come back to and really dwell on when we hit chapter 3, so the very beginning of chapter 3 focuses on interpreting and using determinants. A matrix is invertible if and only if it has a non-zero determinant. So another way of phrasing this is the unit n cube in Rn is mapped to some t of, let's call this unit n cube c. The image of that cube has non-zero volume. Or equivalently, no matter what, one of these matrices, if we have a transformation from Rn to itself, our matrix that this transformation comes from is invertible if and only if our matrix T is injective. So we never map down to something of smaller dimension than we started with. All right, in the next set of videos that we'll be looking at, which are going to come up actually for class on Thursday, you guys will have those pop up, we'll look at calculating general determinants and study properties of determinants more generally, seeing how they satisfy something called multilinearity, and how they're going to be the unique function that's going to satisfy 3 properties that we'll be interested in later. So I'll see you folks next time, and have a great night.